Hello, I'm Arun Mehta. I'll start with the explanation of implementing an analog multiplier circuit using a TI analog circuit board to multiply two sinusoidal waves. So this is the signal generator. We have two input waves, both are sine waves. One is 1 voltage peak to peak and 1 kilohertz frequency. The other is 2 voltage peak to peak and 10 kilohertz frequency. Now we have connected the signal generator 1 to X1 pin and we have connected X2 to ground. Similarly, we have connected signal generator 2 to Y1 and Y2 to ground. Now we have connected Z1 to output, which acts as a feedback, and we have connected Z2 to ground. We have connected output to the oscilloscope and we have connected 1 by SF to the negative. So this is what we have obtained as the output waveform. It is triggered but not averaged. We can see that it looks like the product of two sine waves, and we can also see that it has an approximately 1.25 output voltage. Now we have done FFT. As we can see, we have two peaks in FFT. Now we'll move the cursor to find the peaks. The first peak is at 11 kilohertz. It corresponds to F1 plus F2. Now we'll move the cursor to find the second peak. The second peak is at 9 kilohertz, which corresponds to F1 minus F2.
So for the second task, we've implemented a differentiator based high pass circuit. The output of the analog multiplier is fed in as an input to the op-amp in terminal 2, inverting terminal, through a series of 1.5 kilo ohm gain flattening resistor and a 10 nanofarad capacitor. The feedback resistor is also 1.5 kilo ohm and is connected to the output. The non-inverting terminal is connected to the ground, and the op-amp power supply is connected directly to it. So these are the two input sinusoids. One of them is a 9 kHz 1 VPP sine wave, and the second one is a 10 kHz 2 VPP sine wave. The original output that we get after passing through the sinusoids through an analog multiplier is this sinusoid. On analyzing the Fourier transform, we can see that there are two peaks. One of them occurs at approximately 19 kilohertz and the other occurs approximately at 1 kilohertz.
I'm Arjun Anand and I'll be doing the interpretation of results, that is task 3 and task 4. So as we see over here, for the input we had taken 9 kilohertz and 1 VPP, and the second signal to be 10 kilohertz and 2 VPP. Then we passed it through an analog multiplier, and there is the sine wave that we observe. And finally, we passed it through a high pass filter, that is a differentiator using an op-amp circuit, and there's the output that we see, which is just a singular sine wave. Now let's take a look at the FFT of the final output. Here we see that the peak comes to be at approximately 19 kilohertz, which corresponds to the F1 plus F2 frequency component. We see that the F1 minus F2 frequency component has been filtered out. This is due to the fact that the op-amp differentiator circuit is a high pass filter. To understand how we are getting only a singular sine wave in the output, we need to look at the op-amp differentiator circuit. So here we are passing the product of the two sine waves, that is the analog multiplier, and we have a resistor and capacitor in series, as well as another resistor in the feedback loop of the op-amp. So to calculate the transfer function or the gain, we take the ratio of the input and output, which comes out to be the ratio of the impedances, which is minus Z2 by Z1. In this case, we get it to be minus RF by R plus 1 by J omega C. Let's take when we take the magnitude on both sides, we get it to be minus RF by R square plus 1 by omega square C square. When the frequency tends to infinity, we get the gain to be minus RF by R. To determine the filter's bandwidth, we need to calculate the 3 dB frequency. We have a formula for this. We know that gain at 3 dB is equal to 1 by root 2 times the gain at omega equal to infinity. So plugging in the formulas, we get that omega square R square C square equal to 1. So omega equal to 1 by RC. Now taking a look at this graph, we see that the gain should flatten out. And here we have chosen the 3 dB frequency to be 10 kilohertz, as it is serves as kind of a midpoint between F1 minus F2 and F1 plus F2.